Okay, thanks. So this session is titled News from the Modelica Association, and there's actually a lot of things going on in the Modelica Association and a lot of good technical work. For example, right as we have this conference here, there is a face-to-face FMI design group meeting in Berlin where they do a lot of new work regarding the next steps after they manage to finish FMI 3. And that's also why I am going to use this slot to talk a lot more about the technical progress and technical developments that have happened around the Modelica Association in the last years. And I only do a little bit about other stuff from the Modelica Association, like the next conferences and ongoing projects and all these kinds of more formal things. So the overall view for this slot is that I will take a brief one on Modelica Association. I try to even do it shorter than 15 minutes. Then a talk on what's new in FMI 3, and that will also mostly go into what it's good for and why it was done there, and similarly about eFMI, a new open standards for physics models in embedded software. Also about 30 minutes. I think on the technical side for all of these things, I'm not necessarily the expert that knows very much in depth why all these things were done. You know, I'm not the expert on virtual GPUs and things like that. I'm but I know enough about it to understand why things were done and what they are good for. Okay, so first about the Modelica Association news. I start thanking our sponsors again. Talk about conferences, new logos, and then the different projects, the news in these different projects, all of them. And then some links, mostly for you for later on. That's not a slide that we will look at much, but it will be posted. So if you, after the conference, want to go back, you can go back and find a lot of links that could be useful. So first, thanks to our sponsors. Platinum sponsor is Ricardo, soon to be renamed Realis, as we experienced yesterday. So this is not the final logo, but that what used to be Ricardo-software is now has become an independent company, and they are the platinum sponsor for this conference. Many thanks, Mike, for doing that. Gold sponsors are ANSYS, Dassault System, Julia Computing, Modelon, and Wolfram. I choose an alphabetical order here to be fair, since I'm also from Modelon and don't want to do anything that doesn't fit here. And silver sponsor is MapleSoft. Thanks for all the sponsors. Without the sponsors, the conference would not be financially viable and possible. Now, upcoming conferences. The next Modelica conference is going to be the one in Asia, and I don't think anybody from here will go there because that is on the US Thanksgiving Day. It's Thursday and Friday. Maybe the Europeans, some of them might go there, but otherwise it's unusual. So that will be November 24 to 25 at Sophia University in Tokyo, Japan. It's going to be a hybrid conference where even presentations are possible remotely. Here we have that only for the user presentations, but not for any of the real papers. More information is on the website at the Modelica Association. And yeah, there's a number of very good papers that have come in there. And since it's a hybrid conference, if you feel not like shopping on Black Friday, you can instead watch the conference remotely if you feel like doing a night session. Then the next upcoming conference is the International Modelica Conference 2023. And that will be an in-person conference, not hybrid. Hybrid conferences are actually quite difficult to organize if you want to make them very nice. And it will be at the Technical University in Aachen, Germany in October. At the moment, it looks like the most likely dates are October 9th to 11th. And the call for papers is expected soon. We have two people from Aachen here. Do you have anything else to add? Make advertisements for the conference and for Aachen as a nice city, and then yeah, hopefully many will show up there. And thanks for doing that to your professor on short notice. This was really very nice. So then a little bit about Modelica Association news, what has been happening. First, about the past, things that happened since last conferences. We have compliance and antitrust guidelines that were accepted. These are things, these compliance things become more and more important for associations to look at. And they're also not always very simple. It's sometimes quite useful to work quite closely with industry members. But when you have many industry members in one group, you could be accused of antitrust breaking things. And so they are quite important, even though they are the background legal stuff that we usually don't talk about and want. But they actually have made certain collaborations with industry a little bit trickier and more difficult for us. There will be a special issue from the selected papers from the last International Modelica Conference 2021 in the NDPI journal Electronics, which just closed, which are 9 journal papers that are substantially improved versions from submissions to that last conference. And then we have 104 videos from the last conference, which are available on YouTube and the YouTube channel. And eventually, after some period, also the presentations from this conference will end up on the same YouTube channel. And the MA logos, the new ones, are stored on a public GitHub repository. If you want to use them, there are rules for using the Modelica Association logos. You can use them. Under certain conditions, you can find these logos there. Ongoing projects. One thing is really a sore thing, the website of the Modelica Association and the Modelica Association projects. Most of them are not in great shape and look like they are from 20 years ago, which is also roughly true. And there's a relaunch in the works that is moving, but moving slowly. But I think before the next conference next year, we can expect a better, more up-to-date, and actually usable websites of the Modelica Association. There is a working group for standardization and encryption of Modelica libraries and artifacts, SEMLA, that is actually now taking up a little speed. This has been something that I have tried to actually drive personally for quite a while. And that has been developed by Modelon and is proposed to be taken over. We have also a lot of open source code. The repository will be transferred actually to the Modelica Association in the next couple of days, as soon as I find time. But it's going to be within the month of October, I would say, so quite soon. And then it will be much more possible to do that jointly. I think that should enable actually a better ecosystem of Modelica libraries, because that enables anybody that writes a good library to make it available and also make money from it, basically for licensing, by enabling licensing of Modelica libraries to Modelica tools that is independent from the tools vendor. Then a list of ongoing research projects where Modelica Association standards are involved. FIMOS is about proper hybrid models for smarter vehicles. This is really about combining Modelica works with neural networks, machine learning, and these kinds of things, everything that the Julia guys are doing. But it's a European research project. It's quite useful. And it is a largish German research project, actually. AppSim, Unleash Potentials in Simulation, which is really much more about a credible simulation process. So how do you need to set up simulations in large organizations in such a way that everybody, even people that may not be so technical, believe in these results? Set level, safety of automated driving. the safety of automated driving, I think it finishes this year. Most of these projects can run over a little bit. FMI and SSP are core standards. I think this is really about, what, level 4 autonomous driving, you know, the holy grail of these autonomous driving things that is not actually on the road yet. And yeah, this project is also used to further develop the SSP standard. And then Modelica for large-scale physical systems. I think that is now over, but there's been quite a few projects. There's actually new projects in let's say, proposal stages. And I think I would like to put in a pitch here for European research projects, because the EU actually has done a great job in promoting these standards and financing the development of standards. I think that is something that works better in European funded research than in US funded research, and I can really say that since I've been on both sides and been in projects on both sides. So if anybody here is in a position to tell the US to do a better job at that, that would be nice. Yeah. Okay, then what else? This is about ongoing projects within IBIPSA. That IBIPSA is the International Building Performance Simulation Association, I think, is the abbreviation. There have been a lot of IBIPSA projects with Modelica and promoting Modelica standards. There's a Modelica working group now and a new one. If you are interested in that, talk to Michael. You've seen him, one of our organizers. And that is really, I think, excellent work is done, and it's really visible to see that in the buildings industry, Modelica is becoming a more and more accepted standard, much more than in many other industries, and that is thanks to the work of Michael and others, and organizations like IBIPSA that are actually taking over these standards. And then Bob test, and that is mostly by David Bloom. He's also here. Could you reach up your hand? David is there. It's Bob test is for building. It's a test. It's an optimization and testing framework for building controls. That's open source. Very useful project to move the state of the art in building controls. Okay, quickly about the different project news. The FMI project have new project leaders, Christian Bert from Bosch and Thorsten Sommer from Dassault. Very active project. FMI 3 has been released in June. I will talk about the technical side, and I can skip everything else because that will come in much more detail on the technical talk. EFMI project news. We had an alpha release in 2021, and there's been a little bit of a hiatus because it came to alpha at the end of the European research project, and now work is unfunded and therefore much, much slower. But it's still ongoing. It was developed in an EU project, and I would say that all the work about defining the semantics of the standard is really completely done. But it's actually difficult to write the standard well. There's editing work going on. And I hope it will be really finished quite soon to become a real 1.0. There's some early tool support already. And I would say the standard is enough for people to implement, but it's difficult to implement for people that have not been part of the project. And we want to write the standard in such a way that even people that did not participate in the project can properly do that. That is really an editing question, actually. The website is unfinished, but all the information is available through the Emphasis website, and I will talk about it later. So not much news about the SSP project, mostly, but work is ongoing to update it with the current status of FMI 3, and work is ongoing to improve it through this ongoing set-level project. They are collaborating quite closely with ProStep IV IBIP Smart Systems Engineering project, so with a systems engineering community, which I think is great because usually these things, the systems simulation and systems engineering, are very separate, but there are a couple of, let's say, coordination and collaboration meetings. This about newsletter and links is only for people that want to look up information later on, so nothing to talk about. And again, big thanks to our sponsors. And then I will go to the next presentation, which will be about FMI3. And I just need to switch presentations. Give me a second. All right, so in June, Modelica Association, or the FMI project, rather released the FMI3 standards. And so this is really a talk about new features and new applications. Again, I have fiddled a little bit to make this maybe easier to understand for outsiders, but otherwise all of the material is by others. Mostly Andreas Junghans, the previous project leader, Thorsten Blochwitz from ESI. There's a couple of good examples from Thorsten Sommer. By the way, I have a couple of publicly available Jupyter notebooks, which we demonstrate in practice what the new features mean. I'm not going to show them here because that takes too much time, but if you're interested, you can contact me and I can dig it up and show you later. So, I talk a lot about the motivation why FMI3 was actually necessary, because FMI 2.0 has been incredibly successful. And because of that, new use cases came up. And then I basically go through all the new features in FMI3 and give motivations why they were added, what it's good for, and what to expect from that. And then talk a little bit about the roadmap. Where are things going next with FMI? Because there's really still very active ongoing work. So let me do a little bit of a comparison. On the geometry side, there has been something that has actually contributed to the name giving of FMI, the digital mockup for packaging geometry and structures and parts. So if companies work together, they deliver geometry of their components as CAD data, and it's really easy to compose very complex structures from digital files which are transferred between companies, and they really just fit together. There's been a whole other set of standards in order to enable that, and that has been going on for much longer actually than the Modelica Association. So OEMs can assemble these from the whole virtual system. And you can check consistency of these things, you can compute things, you can compute design envelopes, so it's very useful. But you can evaluate how things can be assembled and disassembled, etc. But there's no behavior in it. And that was basically the idea behind FMI. But with FMI2, we didn't get far enough because this really easy composability and assembly, so you can just compose a much larger simulation just from the units, wasn't quite there in FMI 2.0. And I think also, I mean, taking a step back, I think it was completely right to do FMI 1 and 2 as they were, because in terms of complexity of the standards, it's a big step up in complexity, and it's a big step up in capability also. And so we have now more than 170 tools, known tools. There's plenty of unknown tools and in-house tools actually that support FMI 2.0. And I think the uptake with FMI 3 will be slower because it's a lot more complex. And it's fewer tool vendors and companies that will need the full power of FMI 3. But it is absolutely necessary for the new use cases of really being able to compose complex simulations from simple ones. So when you go through different design phases here, going from concept to design, optimization, implementation, test and verification, and operation, we use models in all of these and models of behavior. And we need to be able to reuse things through these different phases and bring systems together. We want to go from concept to design. We want to go from component design to system design. That is the one step where FMI2 was not always good enough. And then we want to go to test and verification, and that is actually also something where EFMI comes in. And and then finally to operations and digital twins. And on that side, you also have things like MPC, so model predictive control, and that's really where EFMI will come in. So FMI brought us simpler plumbing for simulation. We have the model exchange, which is really ODEs with discrete events on how to connect systems of equations, and FMI for co-simulation to connect any model. This whole FMI2 enabled actually a massive reuse of modeling investment, and has actually, I would say, brought enormous progress to the industry in terms of being able to reuse models through phases and being able to reuse modeling investment. And FMI2 has enabled new use cases, and that actually require then extensions to the standard in order to really get to where we are now. And so the appetite came from the eating, and once FMI2 was there, people then started to have higher expectations of what can actually be done. So what are the use cases that require this? On the automotive side, it was a lot about virtual electronic control units, where FMI2 works quite well for physics simulation, but it did not enable fully virtual ECUs, where in the testing phase, you really want to bring together the physical model and the future controls, but actually in the state of the real implementation, not as a model, but using the actual code and an emulator for the ECU. That's the ECU phase, where you do the validation and the testing, not as model in the loop, but with code that is generated for the final hardware platform, and then executed on an emulator of that hardware platform, and then that is packaged into an FMU and brought into the validation process. Advanced co-simulation. I think I've written an article in NAFEMS magazine a few years ago, with a title which was, I think, Co-simulation, Art or Science, because many co-simulations failed, and everybody that's a controls engineer knows what can go wrong about co-simulation, because you have a delay there, and so you affect actually stability of the co-simulation, which has nothing to do with the physical stability. It's a numerical instability issue, and lots of people that tried co-simulations were seeing that and failing miserably. So the new features in FMI3 really work at improving the situation, actually very significantly in terms of this instability that you get with co-simulations. Multi-FMU simulations are getting more and more common, and so this issue from the last effect was something that more and more people actually ran into and saw, well, this doesn't work as well as it was advertised. I thought as soon as I had FMI, I can compose arbitrary FMUs. Well, not quite. Co-simulation is actually incredibly difficult, and I want to go actually back and make a pitch for Modelica. Use it only if you absolutely must. Co-simulation you pay for very bitterly with lots of problems, even with FMI3, by the way. So if you can develop a system completely in Modelica, that is much easier. Model exchange in Modelica is much more useful, much less trouble than model exchange with FMUs. I mean, obviously there are tons of cases where it can't be done. You cannot put the software as executed, like the VECU case, that cannot be in Modelica. And it's absolutely right to do it with FMU. There's tons of cases which must be FMU, also co-simulation with CFD or finite elements. But as long as you stay on the system side, I mean, I can just repeat what Scott said. reduce the number of tools as few as you can, stay in one framework, it will be so much better. Scott, do you agree? Okay. Okay, and then there's new machine learning and AI applications, and FMI3 will actually help there. All right. I applied labels to all the new features. So if I talk about the features now, if it's VECU, you know what it's for: co-simulation, events, and AI. And so you can track now which of the new features are for which of the use cases that I brought here as a means of simplicity. So then there's also something which is overarching API efficiencies, right? I mean, you can do things in software, you can do them efficiently and inefficiently, and a couple of things were simply done to be able to do things more efficiently from the software engineering point of view. So if you look at models and model exchange along the design V, the VECU is very much on the right side, AI mostly on the right side, a lot for operations when we get real data in. But also you can use it early in the design process to really simplify models. That's actually very much the case from the Julia people. You can sometimes really well use reduced order and AI-based models in the design process to speed up searching a very large design space. Co-simulation and events are on the right-hand side and the left-hand side of the V equally. So if we look at the main features, they can also be sorted in other directions. There's an event mode for co-simulation and intermediate variable update. Those are both for performance and accuracy of co-simulations. Then we have clocks, new types, and array variables, which are a combination between performance, accuracy, and new applications. Then we have terminals and icons, which is really much about making nicer user interfaces for FMI-based tools. FMI for scheduled execution and the preparation of FMI as a standard for layered standards. And that is the ongoing work. And so those are all the new application things. So I sometimes, when I have enough time, I do actually a demo of these things. We don't have enough time, so if you want a demo of some of these things, just come to me and I will find that. So new interface type, scheduled execution, that is needed for VECUs and events. So in FMI2, there were 2 interface types, model exchange and co-simulation. FMI3 has 1 additional interface type, scheduled execution. And that use case is for really allows coupling of several FMUs with one external scheduler, meaning the scheduling of when things are run is more like in software and is triggered by an external scheduler. So you need that. That is a pure control systems question. Yes?
So, for example, it seems like if you want to use an interrupt to start a simulation.
If you want to use an interrupt to start a simulation or run a particular controls algorithm, I would say starting a simulation would be a little bit unusual. Yes, you could do that. That would be maybe slightly. The thing that always happens that people use standards a little bit outside the original intended design, but yes, would work. So FMI3 brings new data types. That is mostly for the VECU type, because the hardware does not use these data types, and that has been one of the biggest problems in trying to use FMI 2.0 in real down the line inside VECUs. So there's lots of new types on the real and integer side. And FMI Boolean, there's one that is really completely new, FMI3 binary, and that type really allows to bring in much more complex data, for example, camera data or LiDAR, anything that is high bandwidth stream data. Because you might want to have, an FMU in the loop when the sensor data is actually images at a high rate, like from a LiDAR or from a camera. All the other ones, they are typical data types for that are used in control system programming. Okay. Oh, I have one more comment on my text here. The FMI 3 binary is really very, how should I say, very primitive inside the standard. You need metadata in order to be able to interpret what the FMI 3 binary type is. You know, something needs to tell you that this FMI 3 binary type is a video with a frame weight of whatever, 24 pictures per second, and that size of the frame, and all these kinds of things. And that is not in the standard, but there is a way to describe that in metadata. So array variables, vectors, and matrices also for the ECUs, but also a lot for API efficiencies. In FMI3, variables can have multiple dimensions. An element in each dimension can be either constant, specified with a start attribute, or changeable. Then it's a structured parameter, and then it can only be changed in configuration or reconfiguration mode. And so FMI3 set and get operators in the API now work on whole arrays in FMI3. I mean, that's a huge thing in terms of the API efficiencies. In FMI2, everything was converted into scalars, and that can be cumbersome. Terminals and icons, that is really mostly about new use cases, because terminals can group input and output variables in the terminals, and which can represent either buses on the control side or physical connectors. So the interesting thing is, you can now make something look like a Modelica model, even though it has a given input-output causality. So if I may take a small poke at one of the big competitors of Modelica, which are old-style C, C++ tools with fixed causality, like AimSim from Siemens, for example. You can now do in FMI3 exactly what tools like AimSim do in their user interfaces, because they have fixed causalities, but they use terminals with connectors exactly in there in order to make it look like it's an acausal connection, like in Modelica. So the main purpose for this here is really to improve the UI, and you can achieve with that you have the same structure and a similar appearance close to the real system, the same as in Modelica, right? You can do a diagram layer built from FMI3 using that. There's actually an effort to backport terminals and icon to the next version of FMI2 as a layered standard, because it is completely orthogonal to that. That is ongoing work, actually. FMI for co-simulation event handling. So if you are one of the probably few people in the room that remember the details of FMI2, when you have FMI2 for co-simulation, you cannot have events. You have a fixed communication interval, and there's no events in between. So now in FMI3, you can have events, and the event mode can be entered by the importer to handle input events triggered outside the FMU, but you can also enter event mode on request of the FMU to the master algorithm, such that the master algorithm can schedule that. There's a capability flag for that, and so etc. And then there are arguments to make sure. I mean, both the FMU and the import. I mean, both the FMU and the importer need to know that both sides handle this event mode, because otherwise it doesn't make sense for really implementation. This is for co-simulation and events. This is one of the things that I can demo on request. FMI for co-simulation intermediate variable access. That is only for co-simulation, and that really addresses the issue of the time delay and the stability problems that you get with FMUs for co-simulation with an embedded system. Because typically you can have an added time delay of the communication step size of the FMU that can cause real bad troubles on stability. But with this intermediate variable access, you can actually, the master can build much smarter co-simulation algorithms that can make use of, for example, derivative information at intermediate points, and so you can use extrapolation in a much safer and much more efficient way. One thing that I'm not so happy about, there's actually quite a few patents out there that basically need this feature of FMI to do co-simulation. So all the companies doing these master algorithms, I find that quite unfortunate that some have actually patented that. I find that not okay from the Modelica Association point of view. We put in the work to provide a standard that makes it possible. I don't think it's okay to then build patterns on top of that. I'm not okay with that, I have to say. But that's the way the system works. So this enables quite a few use cases: advanced co-simulation using interpolation, extrapolation, transmission line modeling in co-simulation. It's a particular way, yeah. If you Google that, you will find plenty of papers on it. Yeah. You can also do much better plotting of simulation results using additional time points. So you can make a plot look much nicer. That's also something I could demo, but after. Then we have clocks. I mean, one of the good reasons for clocks here is that we have clocks in Modelica, and we didn't have since some version back, and that was introduced about the same time as FMI 1 and 2 came about, I think between 1 and 2, but not with the first versions of FMI. And clocks really can synchronize FMUs with the importer and with other FMUs, and the synchronization is much more efficient than what was possible in earlier versions of FMI. It's for DECUs, co-simulation and events. And it's also used a lot in the scheduled execution. So for scheduled execution, you can synchronize things across FMUs, which was otherwise really quite difficult. There are different clock types: time-based clocks and trigger clocks, periodic clocks, aperiodic clocks. Also, for this whole thing, I will not go into the details here. There's many examples. I suggest if you are interested at this level of detail, you look at this once it's posted at the conference and you ask people which are really into the details. This is really mostly for people working on the embedded side with integrating controls. Otherwise, for pure physics simulation, you basically don't need the clocks. So I think I have the wrong audience to go into the details actually. FMI3 will offer adjoint derivatives, which is mostly for machine learning and AI applications. So you need in AI applications vector gradient products, and they can be efficiently implemented using reverse mode automatic differentiation, and FMI3 provides access function for the partial derivatives there. So this will allow to much more efficiently train AI models with FMUs, basically. And I think, I don't know if you guys on the Julia side have already implemented that. I would assume so, right? I mean, yeah. Yeah, so this really is much for enabling the combination of physics-based and AI-based models and training of AI-based models based on FMUs, and doing that in a unified framework. Okay. Next one, the concept of layered standards. I think this one is actually very good, and people should really think about this, because I think there's even an XKCD comic about this, you know, about how many different standards are available for something, and people doing a new standard when you need one, because it doesn't quite fit, etc. So I think we've seen in the past, in the general area of technical standards, quite often that somebody came with a new use case and the old standard didn't quite fit for what they needed to do, and so they developed a new standard, and so instead of having one standard, you now have two competing standards. And you know, if that proliferates, it really doesn't work at all anymore. And I do think that this concept of layered standards could make that less common and superfluous much more often, because it is possible in a much easier way to add on any concern of importance that people want to standardize in a way that is compatible with the FMI standards and not competing. And I think, so from my point of view, you know, being in this industry for 25 years or something like that, and watching this, this actually has the potential to really be a little bit of a game changer and stop this game of competing standards and instead really come up with collaborating standards in a much better way. Okay, philosophy off, back to the concrete case of why it was done for FMI 3. XML element annotations, for example, that allow additional semantics for variables and terminals. There's an extra folder in the FMI zip file that allows to ship additional files with the FMU. So there is actually very well defined storage space inside FMUs for these layered standards. So it's easy to add standards in a way that does not collide with any other standard, that can be supported and integrated. You can do that basically completely without the Modelica association. And if it catches on, it catches on. And you only need to remember the naming convention. Then the Modelica association themselves will work on a couple of ones, which are really important. And so the meeting that is currently ongoing or just finished because of the time zone difference in Berlin was really about moving forward with actually working on layered standards for FMI 3. So XCP is about packaging virtual electronic control units. XCP is a standard by a different standardization organization called ASAM. They do standards only for automotive cases, and they work with ECUs for cars, and XCP is a standard that describes a standardized access to the ECUs and how to handle them. And that is obviously quite orthogonal to what FMI does, and so you can actually package it as a layered standard. It's in preparation in the FMI GitHub. Another one, network to signals, allows grouping and description of FMU inputs and outputs as network signals, also in preparation. You can include 3D visualization in FMUs, which represent multi-body simulation. There's a prototype from ESI-ITI and the University in Dresden. And you could also include fully orthogonal standards like the many competing standards, which are currently on the way to describe metadata for models and modeling. There is one that is an ISO standard, also developed from a European project, and the project was called MOSIC, and I never remember the ISO number. And there's another competing one, MIC model identity card, coming from mostly the French automotive industry. These things can now also be included, and mean metadata. There is a little bit of metadata in FMI, but the metadata that they want about what the model was done for, that is not in FMUs, but it can now be included. Yeah, miscellaneous ones, which I think I will hop over. There was one simplification. There was an asynchronous execution FMI do step that has never been implemented. Actually, one noticeable one from these miscellaneous ones is really improvement and clarification of source code FMUs. Those are actually quite important for the aerospace industry, where they think that they really need to be able to resurrect models after 30, 40, 70 years. And so that is actually a very tough problem. If you think back in computers, 50 years. Okay, I'm not going into the details. It's difficult. Okay, roadmap. What's happening next? The FMI 3 has been published in May, and one thing I would like to add there is that because of continuous development and testing of prototypes, the quality of the standard and the standard text is much higher than it was actually with previous versions of FMI, and I think pretty much with every other standard out there, because that is very different how the Modelica Association works with standards compared to many other standards organizations. They usually work in such a way that first the standard is done, and then prototype implementations are started. FMI 3 took so long because the prototype implementations were developed in parallel to the standard. So nothing was standardized that wasn't actually tested, which leads to much higher quality overall. I mean, I would give that a little bit of a, step back on that. Not all the features have been implemented and tested in combination, but each feature has been implemented at least once by one or two implementers, usually in a way that you can test an exporter and an importer. But not in all possible combinations, which still might show problems. I mean, doing standards is difficult, and you always have the compromise between complexity and difficulty and how broad you want the standard to be adapted. I think FMI 2 was a fantastic compromise on the simplicity. FMI 2 was 70 pages of PDF. Now it's all web-based and online. I think one competing standard that I found in a different industry that is actually almost not implemented for a similar purpose for architectural models had 700 pages. So I think actually, the 70 to 700 pages makes a big difference in terms of how easy it is to adopt these things. And then what has helped FMI quite a lot is that there were quite a few open source implementations out that really helped with spreading that. Okay. Oops, I pressed the wrong button. Okay, sorry, roadmap. One more important thing. There will be an implementer's guide for FMI 3, which is almost finished. You can go to this GitHub link, so Modelica, GitHub.io, FMI guides. There is an FMI guide, there's a GitHub page, and there's a web page which shows it. So the implementer's guide was actually paid work by the Modelica implementation to help anyone who wants to implement FMI 3 to do that efficiently and well, with examples and guidance and so on. That is also something that the Modelica Association has taken from other standards organizations. That has been necessary there much more because prototypes were also done after, so you need an implementer's guide in order to help people. And then work on layered standards is on the roadmap. Resources are for looking later. More information, also all the kinds of tools. These links are here for people to look up later. You don't have to go through that. Okay, I think I went slightly over, and I think EFMI deserves as much time. So. Okay. Actually, you have to suffer me for quite a long time here. Okay. Okay, EFMI is a new open standard for physics models in embedded software. Why? Okay, now I start with something slightly more relaxing. I hope this works. I don't know if the audio works. I actually. So this is a video from Bosch about ESP stability control. Yeah, I have the audio actually off, so, and I will just comment this. Bosch deserves really credit because and that's why I'm showing a video from them about ESP, because they were really one of the main driving forces behind the EFMI standard, and that may become obvious. So, what is ESP about? It's active safety in cars. You need to actively react to dangerous situations and stabilize the vehicle. And in order to do that, you need models inside of the car, inside the system. So this is a situation: you drive on a highway, and nothing's happening. Go driving, you get a little drowsy, and suddenly something happens, and then your car starts spinning. So ESP is basically about trying with controls, smart controls, to avoid this situation. And so this is now the same simulation, but with a vehicle that has an active ESP system inside. ESP is an electronic stability program or something like that. And then the controller actively starts really reacting and doing stuff. So there's lots more situations where ESP can come in, and this video goes for longer. I want to stop that. This was just a little bit to start. Why do we need models in embedded controllers? Okay. So, and that is really an old story. Since the early 70s, people know that every good controller of a system needs to contain a model of that system, the internal model principle. And Scott probably knows and has read a lot more about that than I have, having taught controls for quite a few years. But back to ESP, you need actually two components of the overall system inside the controller in this case. You need a virtual sensor to detect the system state. I mean, and the state is really relatively complex in that situation. What is your, mostly the acceleration in all kinds of directions, and you need to make sure to stabilize the car. You want to keep these accelerations within certain bounds, and when you start to spin, circular acceleration, you want to stop that. And the ESP does then actuate brakes on single wheels to, for example, when it starts spinning, the brakes produce a counter torque to stabilize the vehicle. What that does is that the vehicle starts to behave as the driver wants it to behave and not start spinning because the vehicle's lost control. So you need two things there. The virtual sensor, that is typically something like an extended Kalman filter or something like that, because you don't have exactly the right sensors and you need to get from some sensors to the real state. And then you need an inverse model of the vehicle dynamics to apply the controls in such a way that the car does what you want it to do instead of what the inertia and physics or whatever make it do. Okay, so enough motivation here. Advanced control is challenging. The title could have been the title of yesterday's keynote talk. We know advanced control is challenging. So, and online physical models, or models which are inside these controllers, are key technology for advanced control software. This has come from the automotive industry. I mean, it's a big industry with a lot of money, and safety is very involved, but this holds for actually all other industries. There it's much more about efficiency, but in aviation it's the same. And what we want to do there is really want to be able to injecting the magic potion of physical models into controllers. MPC is something like that, yeah, model predictive control. That's when we have nonlinear MPC, we have actually nonlinear models in the loop in the controller. And The problem is a little bit that these worlds of physics and embedded controls are very different. They talk in different terms, the people don't understand each other, it's very different standards. So what we want to bridge the gap between modeling and simulation, where we figure out what the world is doing and try to recreate that. Great talk from Dirk this morning about that. And then we have products in the real world which we want to control through embedded software, and we need to get these things together. So the state of the art there for people that develop controls is that they really need to understand everything. They need to understand the physics modeling, what is the right model for my controller. They need to understand controls engineering, so they build stable controllers, not the unstable ones. We also saw yesterday in the talk that can sometimes happen. They need to understand numerics, because if the numerics of the model won't work, the embedded controller won't be stable. And they need to understand ECU software. That's basically a functional developer needs to be a superhero. So the idea of EFMI is to really be able, by a smartly done standard, to separate these things. And what we want is that instead of a superhero, we can have physics and experts and control engineers, all the numerical stuff we would like to put into services and libraries which are pre-packaged and reused, and we have ECU software developers. And in that way, you know, it is actually possible in finite time to build an advanced controller and put it on a device. And I mean, we've heard Scott about how difficult that is for many of these things and how long time it can take for industry. So that's what EFMI is for. And we don't need the superhero anymore. So I'm now bringing in actually EFMI in the D model, so the systems engineering point of view. And I'm stealing slides by permission from ProStep IVIP, which is a European non-profit organization in the systems engineering domain, trying to coordinate standards there. So this V model is a little bit too complex for my taste in this talk, but I think it's useful to see how other organizations and people see FMI and EFMI. So everything that's blue is FMI as it's today, and the blue dashed lines are a little broader here, FMI to B. And there is a next step where they see that EFMI really helps and makes this more useful. So ProStep IVIP is also promoting the EFMI standard and the EFMU. So the scope of an EFMU is also something that's important, is one software component, a controller or a virtual sensor, as part of a cyber-physical system. So the final system could be composed of, or could need many EFMUs. You know, it's one software component inside a complex cyber-physical system controller. So yeah, there's recalibration steps for EFMUs when you adapt FMUs to real data once you have real data of the system data in the design process. And the EFMI behavior model is a container that allows you to do much better validation and verification of your controller, and in particular the model inside the controller from your use. Yeah, so it really helps to go to promote a faster process through this design wheel, where the EFMI binary code container allows to do functional tests and hardware in the loop. So I will go now for more details here about EFMI and embedded software. So this is specific to automotive industry, and EFMI was developed for automotive. I think it is at least as useful for many other industries. And it may be that special and more tooling is needed, but the requirements from automotive, they hold for the same for HVAC, I think, or many of them are the same in the HVAC industry, as we heard from Scott, which is why they are part of the EFMI development group, and it holds for aerospace. It holds for really many industries. Some with very slow dynamics, you don't need that in that respect. But so you have specialized hardware with limited computing power and limited memory. It needs to be really cheap. It's single precision computations, which always gets you already a difference. You have a limited sampling rate, you have no exception handling. That is extremely important on the numerical side. No, you can't, if you do an ADS break, you can't have a division by zero error. Right? I mean, there was this one, what was it, an Ariane rocket that blew up in space, was a division by zero error on control software many years ago. So these things have happened, and you know, there are actual accidents that have happened because there were no good standards, and it's very complex to write this software. And if you overlook a single case that can occur in reality, your rocket can blow up. So in automotive, again, you have specialized hardware. You need to take into account software architectures, and you have sometimes quite strict rules and regulations in regulated industries. So there's this MISRA, Motor Industry Software Reliability Association. They have rules about how to do safe embedded software for cars, and these need to be taken into account. Okay, and guarantees. So this slide is mostly to make sure people don't mix up FMI with EFMI, because it is quite different. The name has been stolen mostly for marketing reasons because FMI was so successful, and I think it's useful. It's the same association taking care of the standard, and there are enough similarities to actually justify that. But if you look at the implementation details, things are actually quite different. FMI has a standardized C interface. You can have source code, but you always have source code on the way to an FMU, typically in C. You can use other languages. There are no guarantees. If you get an FMU, buyer beware. It can crash anytime. There's absolutely no guarantees. But on the other side, in embedded software, we want guarantees, and sometimes we must have guarantees if the ruling bodies say so. So that is really very different. So EFMI has a standardized logical interface with some very simple prescriptive steps about startup, recalibration, and do-step. It's very simple. And this logical interface is described by a new language called GALEC. I think that's part of algorithm language called embedded controls. And I would say that this GALEC language is the most important and best innovation and real innovation that was developed within the standard, because it didn't exist. And GALEC, I think, is the core piece in making sure that you can actually separate the concerns from the modeling and simulation side and the embedded side. So the GALEC code is not something that is going to be executable and executed. But it's basically an intermediate step in transforming something from something that has no guarantees and can crash at any time on you into something that you can put in the controller and has real safety guarantees. And then EFMI has an implementation interface that tells you how things are doing. So then let's look a little bit at EFMI in collaborative software development. Again, this is an automotive case with OEM supplier and going back and forth between these different steps. So in terms of traceability, you can have a situation that some functionality should be implemented, and you have an exchange of algorithm and production code between OEM and supplier back and forth. And then things are tested, and if something goes wrong, if there's an error, and you try to test back what happened, there can be lots of possible errors. Was it, I mean, you know, you have development cycles which are iterative, so did everybody really use the right version? How do you know? You know, it's actually quite difficult to trace these things. Was the correct code integrated? Did they get the correct model? Many steps along this line of back and forth communication can go wrong. And EFMI really helps with that. Because To have that, you have checksums and possibility checks and consistency checks, and that way you can know exactly where things go wrong. So, if you have the situation that everything is correct on all the fronts, the FMI manifest, the manifest of the behavioral model, the algorithm code, the production code, the binary code, well, if everything there was consistent, then the problem must be something with the original model or controller, but not something that went wrong in the process, because a process can be checked at every step in terms of all these transformation between codes. But there can be other cases. So you know, all consistency checks are done. Everything's fine. But if you, for example, do a consistency check and there is a checksum that fails on the production code side, then you know that the production code has been manipulated after delivery, which could be valid reason, at least in former times. And there may be issues with the tooling, that not everything is fully automated. Something has to be done by that way, and then you need to upgrade the tooling to make it really right. But it is possible, definitely, to see where things went wrong on the process side. And everything else is right, but on one step you have a wrong checksum, you know exactly where it is, so you improve traceability. If you have an invalid checksum between algorithm code and production code manifest, and everything else checks green, then you know that the production code is outdated and does not correspond to the algorithm code. So somebody in the process chain forget to do a new build of the production code and actually include that. So it does really help with traceability. Let's go back a little bit to FMI architecture and workflow and how this is envisioned. So everything here, I do green the modeling work and blue the embedded world, and some of them are really overlapped and overlapped. We have a model which is typically acausal if we come from the Modelica world, and then we simulate the model, and what we can do with a simulated model is we can create a behavioral model. A behavioral model is actually nothing else than the data of the simulation results. You have a given input scenario, and you get result traces, and those are actually put inside the EFMU, because you do so many transformations that at the end, it is really quite difficult to know, is this really close enough? And so you can embed the validation data inside the model, and you can do that obviously for many scenarios, because one scenario might by far not be enough. You can embed 15 different tests of scenarios that the modeler expected to run well in the behavioral model, so that much down the line on a different hardware, and with maybe even moving from floating point to fixed point operations and things like that, you're still getting behavior that is close enough to the original. Then here comes really the basic idea of EFMI, that the modeling and simulation world, the tools there, can generate algorithm code in the EFMU through a transformation. That is this garlic code, which is target independent, but it has one big change from the Modelica side, it's causal. You can also come from other causal languages there, obviously, or acausal languages. This is not confined to Modelica, but typically it often comes from the Modelica world, obviously. So what we want with that transformation is to find a causal upper bounded solution algorithm for a particular model. It actually uses a specific algorithm there. So, or a specific integrator. You actually add an integrator. The algorithm code, the garlic code, is based on inline integration. So, at that point in the garlic code, you know whether it's explicit or implicit. Implicit obviously has often troubles and issues in terms of absolutely guaranteeing that numerically nothing can go wrong, but it is possible to do, and it's also possible to do do even implicit code writes. Yeah. Comes the next transformation, and this is a reason for the Garlic code. The people that know how to build compilers for embedded architectures are not the people that know about numerics, and not the people that know about models and physics. But they do know how to create code that doesn't cause exceptions on embedded hardware. So this would actually typically be different tools that do the transformation from a Garlic code into production code. And in terms of having these, and then you can test this EFMI code and verify, you can run code checkers and verification on these kind of things, and do software in the loop simulation if you compile it back into a software that runs on a PC. And then you have another transformation which creates a binary code FMU, and that can execute on the target world and target FMU. So there is an EFMI relationship between the FMI and FMU and container structure. It is possible to embed an EFMU inside an FMU. So you have simply the whole FMU and you wrap around classic co-simulation FMU with binary and source code and a model description. The model description is a little bit duplicit and superfluous because there's much better information inside the EFMU about with its different manifests in terms of what this data means, but it obviously needs to be there. And because of the broad support for FMI, this is the easiest way to really allow to do the testing and verification in these 170 tools that we already have. So EFMI standard toolchain and workflow. You would have a model, and what you then do is that the modeling tools, whichever they may be, AIMSIM, Dymoa, Simulation X, Model on Impact, other ones, they create a behavioral model for the verification, and that can be several, for many different scenarios, and the algorithm code, and the EFMU manifest. And that starts the whole workflow. And then, as you move on, you bring in new types of software that actually go on and produce production code, and possibly binary code, which then needs to actually comply to standards like AUTOSAR on the automotive side in order to get that together. And that is a completely different set of software. So TargetLink is by DSpace, Scope Congra is a tool by a company now owned by Bosch. And also here we have the possibility of having several binary codes. So one EFMU can contain code for just a normal PC, Linux or Windows, and then you can run your seal tests, and for the actual embedded target. And that both should be compiled from the same algorithm code at least, and possibly and best from the same production code. I mean, that depends on whether, that gets into details. And then once you have these things, you can actually do code analysis by software tools, which are for code analysis and testing, and you can bring it onto the real hardware and do system integration, do hardware in the loop or rapid prototyping. You can do all the good things to validate that concept. The starting point for all of this great workflow is the Garlic program generated by the modeling tools. And that is really the key part that enables the separation of concerns and to get rid of the superhero and instead have modeling experts on the modeling side and embedded experts on the embedded side. Then obviously you get into an iterative development here, and in order to enable that, you can wrap this FMU around the EFMU. That makes the exchange easy. Okay, so I think I've done, I might almost be over time here actually, and not quite done. But I think this is really the core of the standard. I think I've given you the meat of what you would want to know about EFMI and why. And the rest of the presentation is really about everything that has been done to make sure that we actually did the right thing with the EFMI. So there's been an enormous amount of verification and validation effort. There is a library of validation cases from trivial to large and hard. A Modelica library is 22 test cases and 43 variants. There are a couple of AIMSIM models to go through this whole thing also with C code, and some manually written Gala codes, which allow very specific test cases, which are maybe difficult to generate from models. And testing was really set up to cover a large range of typical examples and challenging examples. Unfortunately, a lot of the information of what was done on this verification validation efforts is non-public because it was done in these projects, and so that is only shared between the projects published in the emphasis project. But I think the outcome and what is public about the FMI standard is actually very good, and everything that the Modelica Association was involved in is public, and many of the public institutes. So the DLR, I think, has been working mostly with the Modelica library, with the test cases, or contributed a lot. And a couple of the companies that have contributed. But that library is really a great asset for anybody wanting to implement. So more than 500 test scenarios, and an EFMI compliance checker has been integrated. Quick one on performance. Performance comparison was done to handwritten and optimized code, and with many of the test answers. Also the memory footprint, important for embedded, and error handling, faulty sensor inputs, and all these kind of things. And validation that you can really do the maximum execution times. There are specific tools for that, has been done for everything there. So there's been a lot of work gone into validating that the standard is actually able to do what it was supposed to do. And sorry, the results, yeah, memory footprint was good or comparable to hand optimized codes. Many examples ran faster. I would actually say most than hand optimized codes, somewhere about the same speed and somewhere slower, but nothing was more than 30% slower. And all tools were early prototypes. And so I think that is going to improve as time goes by. There's two EFMI support tools which are public at the Modelica Association GitHub, and an EFMI container manager, so making sure all these, this container structure really works, because you need to actually add things to the EFEU over time. Yeah, you start with the Garlic code, and then you add production code, then you add a binary, and then you iterate these things, and the information and the manifest always need to be consistent. So that is what this EFMI container manager does. And then there's a compliance checker to check whether the implementation is correct. Yep. There's quite a few members of this EFMI consortium. Many thanks to Mitsubishi Electric for coming in as a first non-automotive or vendor company there. I think that is great, it's very useful. And I hope actually other industries to join that. There will be a website, efmistandard.org. At the moment, it still points back to the emphasis website. I'm the deputy project leader. Project leader is Christoph Bürger from Dassault in Lund. And yeah, we're looking forward to actually publish a final 1.0 version of the standard. But don't be afraid. What you can find now is absolutely good enough to work with, actually, for everybody that plans to do something about it. How to get started, how to join the project. Well, here, if you want to join, contact me. And you can contact either Christoph or me via email. And we hope to have the website up with teaser videos, etc. So there are actually a couple of teaser videos have been produced to do promotion for that and really spread the standard. Okay, that was it. Thanks. That was it. And so if you are interested, in the demos, come to me. And otherwise, questions also. I mean, maybe questions now. This was really maybe information from the fire hose. But
I don't have a question. It's more like an additional information. If you're also interested in the EFMI standard, you could get the examples, the one that showed that was on Dana pages. You can get more information about the test cases as well. So, just an information.
Are the examples for the, not for EFMI, but the FMI available also in the Modelica Association, or are those available in the Torsten's?
Yeah, I mean, yeah, some public cloud site where you can run those.
But they might be in his tool, right? The FMI website.
I mean, here's a GitHub site. So if you go to Torsten's GitHub site,
Is the CATIA?
I'm not sure it's on the CATIA Systems or on his personal one. I think it may be his personal one. It's on the CATIA Systems side. So it's on the CATIA Systems GitHub side. You find links to Jupyter notebooks. Yeah. That demonstrate that. So, what you need to talk to hardware, I mean, what you get from EFMI on the modeling side, you know, I mean, I know you do modeling. You need a modeling tool that generates EFMI code. And then you need somebody that can generate production code from the Garlic code. And that is, there are quite a few tools that do that on the automotive side. And if your industry is able to reuse automotive hardware, it tends to be very cheap, so it's useful, then there are also tools for that. So, I mean, I think my recommendation for everybody here to do that is to simply take advantage of the cheap prices in the automotive supply chain and just steal the hardware, and then you suddenly also have the tools for that. I mean, I think that's my only idea. I think that will not be possible for aerospace because the requirements and the standards, etc., are different. So on the aerospace side, I think you will have to find an aerospace hardware compiler builder that wants to tackle this transformation from Garlic into production code. For all other industries, I recommend steal automotive hardware and use it. I mean, that is done. I know that even, on the hardware side, that even aircraft engine manufacturers steal automotive hardware, or they at least use really the same processors, maybe in a different integration. But that would still hold for this tool chain to fully work. You know, the binary will work on that hardware, even if you, so, or make sure at least, I think you can also, I don't know really, I mean, hardware has many different levels, you know, you have the same processor, and then you have other things like I/O, etc. stuff. I think this production code, binary code, etc. thing will work, maybe with less efficient tooling, as long as the actual processor is the same as in automotive hardware, but not the total packaging. So this is but here I'm just talking on the try it. This is not my domain of expertise, but I think that would work for many industries. Also, yeah, you guys in HVAC. Okay. Thank you for your patience. This was a long presentation.